All right, so we're just going to recap with our introduction into the respiratory system. We were looking at the phases of respiration, and we summarized mechanically and physically what happens during inspiration or breathing in, and then what also happens during expiration, or what you would call exhaling or breathing out. And just to review for you, it's during inspiration that our muscles actually contract, including the diaphragm and the intercostals, so that we increase the volume around the thoracic cavity. Okay? And the effect or the change is that we create that volume change leads to a pressure change in the respiratory system. So we can drop the pressure and let air move into the lungs. Okay? Therefore, we can breathe in. The reverse would be true during expiration. During expiration, maybe opposite what you were thinking originally, is expiration is just the muscles relaxing. Okay? And as they relax, the chest kind of depresses and the diaphragm goes upwards, kind of deflates, if you will, so as to squeeze on the thoracic cavity. That drop in volume leads to this increase in pressure, so that the pressure is greater in the alveoli than it would be in the atmosphere. You want to push the air down at pressure gradient. When we inspire and expire, okay, those concepts are plotted for you in figure 1610. And you should be able to hopefully appreciate this inverse relationship between pressure and volume. If the volume increases, the pressure would decrease and vice versa. Okay, so it's an inverse relationship. But we're continually moving air in and out, so our pressure is continually fluctuating. It's kind of implied as it's kind of up, down, if you will. And just a normal tidal volume, it doesn't, there doesn't need to be a huge pressure gradient to move the air into or out of the lungs. Just a millimeter of mercury is enough to move air in and out of the lungs, as illustrated here. So our atmospheric pressure is about 760 millimeters of mercury. So about 759 drop is enough, right, to move air in. And then to push air out, it only needs to go up about +1 millimeters of mercury in respect to the atmosphere. So you could say 760, you could say 761, or you could just say +1, -1, right, whatever the case may be. Does that make sense? The +1, -1 in respect to the atmospheric pressure if it were at 760. What questions do you have about this relationship, this inverse relationship between volume and pressure in the lungs? Did we talk about the relationship between the pressure gradient and the resistance factors? No. All right, so let's go back and review this. This formula, right, don't let it panic you. It's telling you something, a concept that you're already familiar with. The concept is very like what we learned in the circulatory system. In the circulatory system, we are trying to distribute blood, or have blood flow. And in the respiratory system, we're trying to distribute air, so airflow. So just like blood flow, there is a direct relationship to the pressure gradient and an inverse relationship to any resistance factors. The exact same concept applies in the respiratory system. The bigger the pressure gradient, what happens to my flow of air? More flow. Okay, so same thing. There's a direct relationship between the pressure gradient, as summarized here, the gradient between the atmosphere and your alveoli. The bigger that difference is, what? The more flow, the faster, right? So what we conclude is the larger the pressure gradient between the alveoli and the atmosphere, the greater the airflow. Conversely, if there are any resistance factors, our airflow would decrease because the relationship is inverse. So this formula just kind of simplifies that concept, hopefully. Simplifies that concept. Now, let me address a little bit about the resistance factors. What do you think is going to be our biggest resistance factor to the flow of air? What do you really think is going to have the biggest impact to resisting flow or distribution of air through your respiratory system. Volume, stretching, those are important. Those are important. Not the path I was going though, but I know you can't read my brain, so what else might? Some type of obstruction, which decreases the what? The airflow and the diameter, which changes my airflow. Okay, so where I was hoping to go is the diameter of the air passageways have a direct influence on the flow of air. We can change the diameter of the airway, some of them, pretty quickly. Very analogous to like we could around our arterioles. Relax or contract some muscles around the respiratory system to change the diameter. If we look at the resistance and review our anatomy of the respiratory system, going back to figure 16.3 that we looked at last time, we looked at the diameter changes. Where did we see that the greatest change or plummet in diameter, lumen diameter of our conducting zones? Yeah, it's called the smaller bronchioles, right? That's about as vague as you can get, but they're smaller, right, in diameter. You notice we plummet from about 8 to about 1 millimeter in diameter. Previously it was like 10, right? It goes 35, 20, 12, you know, so it's kind of moderate. And then we just see it kind of fall off in the diameter at the smaller bronchi. The smaller bronchi provide the greatest source of resistance to the airflow. Why did we say this is important? On Tuesday, so we can take that, transition the flow of air to nice and steady, or the word we used was what? Laminar or constant. We want to transition it, so the resistance is there to transition that air from turbulent to laminar. And that resistance is just due to that drop in diameter. And so that's a natural, normal, right, resistance factor. It's going to be there. So it actually, there's a use to it, transitioning the air to nice laminar flow. But outside of that, we can also alter the diameter of the upper, right, structures by just some smooth muscle, constricting, dilating, whatever. So we can control the diameter of some of our bronchi in the respiratory system. But also noted you could be sick, right, and have mucus in your respiratory system. What's that going to do to your resistance and diameter? The diameter of your decrease and resistance is going to go way up. So if you've got pneumonia, it's going to be so high that maybe you aren't respiring enough to even keep you alive, right? So it could be life-threatening in those scenarios. But those are extreme scenarios. But in addition to our resistance factors, we can look at what's called compliance. So if we transition to page 5 of your handout, your guided notes, we can talk about the compliance of the lungs. And a real simple way to define compliance is well, how well can the lungs actually expand to fill up with air? Okay. And there are two things that oppose the lung compliance, okay, how much it can stretch. And this includes elasticity and surface tension. So if I want to fill the lungs up, I want them to be compliant, right? I want them to stretch out. However, our lungs, yes, they do stretch out, but they also have a natural tendency to recoil because not only do we want our lungs to fill, we want them to empty. And so we have a normal set point range of elasticity of recoil. But if it becomes so high, our compliance would go down. Okay, so if our elasticity is so great, we wouldn't actually be able to stretch them out. And so, elasticity is there, it's going to be present because we want to have the ability to empty the lung. And so we've got to have a mechanism, and we do, our muscles and etc. can overcome that elasticity, right, to stretch and fill that. Another opposing factor to lung compliance is surface tension. We know that surface tension is present due to the moisture present in our respiratory system and lining the alveoli just to facilitate the function of the alveoli. So surface tension would actually allow the alveoli to do what to one another? If we've got water lining the surface of my alveoli, what would the alveoli do? It would stick together. So the more they stick together, the least compliant my lungs would become, or whoever's lungs would become. The surface tension's there, right? Elasticity's there, but our lungs aren't going to just collapse because they recoil and have fluid. So we have things to kind of get over it. And what we have to deal with the surface tension is something called surfactant, which we became familiar with a couple weeks ago in lab. So let's say that where does surfactant come from? Very good. It's the type 2 alveolar cells that are there in the alveoli and produce for us surfactant to help reduce the surface tension to make the lungs more what? We want our lungs to be, big word? Compliant. We want our lungs to be compliant. So a better visual, although not a biological visual. Do you have your favorite pair of blue jeans? Okay, that you've had since like 8th grade? Right. Let's be more real. Since last spring. Okay, these are your favorite pair of blue jeans you've had for a couple of years maybe, right? I refer to like your Sunday jeans. Okay? They're pretty compliant, right? You can put them on, you feel good in them, and they fit, they don't fall off, they're not so uncomfortable, right? They're compliant. Okay? So they have the ability to stretch, they have the ability to maybe be tight, but you've got them just right where you want them to be. They're very compliant. What would happen if your pants, your Saturday night pants, are they very compliant? No. Okay, so the probability of getting into them takes a little more work, right, to get into them. Do you want your lungs to work so hard to fill up? No. So we don't want them to be non-compliant either. But we don't want the reverse. Okay? We don't want them to be so compliant that they fill up but don't do what? They don't. We want them to. We don't want them so compliant that they fill up but don't what? I couldn't hear. Recoil and empty. So in the jean example, maybe your pants are so big that they're not working as pants. And your lungs, if they were so compliant, they wouldn't work as lungs. So we have these opposing factors. There's an ideal kind of set point of compliance for the lungs. So they stretch and then recoil as well. Are you okay on those concepts? Those are the primary things that I wanted to address on Chapter 16. If you make a quick reference to Figure 16.4, it gives you an idea about the surfactant and the surface tension, which I think we've hit pretty good between lab and lecture. With that will transition us to Chapter 17, and we're going to look at 3 primary things here in Chapter 17. We're going to review the partial pressure gradients for each oxygen and carbon dioxide through the pulmonary and the systemic circuits. And if you have your handout number 11, you can, if you don't have it, you can pick it up from the folder. So go around with the sign-in sheet, and if you didn't pick up your handout last week, so we're going to review the partial pressure gradients that exist, right, for each carbon dioxide and oxygen between our pulmonary and our systemic circuits. We're going to talk about the mechanisms, the way that oxygen and carbon dioxide are transported. We now know, thanks to lab, they're not just transported as just plain old oxygen or carbon dioxide, right? Bound to hemoglobin or something else. And then we'll review a reflex for the control of respiration. Just to review for us, our 2 circuits include the pulmonary circuit and the systemic circuit. And if we want to move a gas from one point to another, we need to establish a We okay? We are super duper busy today. Y'all okay? A minute stretch break or? All right. Just to remind you, when we're transporting gases between our systems at our pulmonary circuit, we need a gradient to basically push carbon dioxide down its pressure gradient into the alveoli and reverse it for oxygen into the pulmonary circuit. When we take gas out, what happens to the pressure for that gas in the blood? It drops. So if I send blood to the pulmonary circuit and I take carbon dioxide out, well, it's going to go to the systemic circuit. So the carbon dioxide content in my systemic circuit is a little bit less. Conversely, if I just added oxygen to my pulmonary circuit, it goes to the systemic circuit, the pressure for oxygen is a little bit higher. Okay? And so we have this constant change between the two circuits. And so by the time we get to the systemic circuit, our carbon dioxide would diffuse down its pressure gradient, and then oxygen likewise into the tissue down its pressure gradient. All right, and so let's just review those pressure gradients that exist between the alveoli and the pulmonary circuit. Keeping in mind what is constantly flowing. So we're just flowing through, so I'm just picking certain points. So as blood enters the pulmonary capillary, we're going to have a higher proportion of what? Which gas? As it enters the pulmonary capillaries, we're going to have a higher proportion of CO2. The blood has just been to the systemic circuit, probably picked up some CO2 and dropped off oxygen. So our CO2 will be a little high in the pulmonary capillaries. Our oxygen will be a little low in the pulmonary capillaries. However, in the alveoli, if we just took a deep breath in, we should probably have a bit of extra, hopefully, oxygen, and eliminated some of the CO2. So we have a pressure gradient. To point out the abbreviation here, the large P, I couldn't get, so on the gas you have a subscript, right? I couldn't double subscript this, so the oxygen should be subscripted on the O below the P to represent the partial pressure. So if I were to able to do this on my computer, I don't know how, I would say the pressure of oxygen. They would call it the partial pressure. If you reviewed that terminology in your lab a week or two ago, the partial pressure stands for what? Partial pressure of a gas stands for what? It represents
What portion of that gas
the portion of that gas
in all of the gases?
in a mixture of gases. So this tells us there's more than one gas present. So if I'm looking at just oxygen, I can say, well, the partial pressure of oxygen is about 100 millimeters of mercury in the alveoli, yet about how much in our pulmonary capillaries as it enters? The partial pressure of oxygen in our pulmonary capillaries is about 40 millimeters of mercury. And then if we look at the partial pressure of CO2 in the pulmonary capillaries, we said it should be higher, a little bit higher at about 46 than it is in the alveoli. So it's about 40 in there, so we have a gradient. Carbon dioxide, each would diffuse down their pressure gradient. So as blood travels through the pulmonary capillaries, CO2 would be pushed down its gradient, and then oxygen should be able to diffuse down its pressure gradient. Does that make a bit of sense? A little bit? We're going to add here in a minute oxygen. When it goes in the blood, does it just stay as oxygen? What happens to most of our oxygen? How do we transport our oxygen? I think I might have heard it. What part of our, yes, it binds to, not that one, hemoglobin. Oxygen binds to hemoglobin. Carbon dioxide undergoes a transformation, but if we look at oxygen, it binds to, most of it binds to hemoglobin, so it needs a transport protein. It's not very soluble. I'm just kind of warming you up. We'll address that formally in just a second. All right, so the pulmonary capillaries take up oxygen and eliminate carbon dioxide because there's a pressure gradient for each of those gases. Is that okay? Any questions? If we look at the blood in the systemic capillaries, we just unloaded CO2 and loaded carbon dioxide, and so our oxygen content should be high and our carbon dioxide content low in the pulmonary capillaries. However, in our peripheral tissues that are actively metabolizing, using oxygen, producing carbon dioxide, their oxygen levels should be a bit low, while their CO2 levels a bit high. These are, remember the linking step and the Krebs cycle produced for us the carbon dioxide. So the values are about the same, but the directionality is reversed. So that oxygen would diffuse down its pressure gradient from the blood into the tissues, your brain, your liver, your muscles, whatever. And then the carbon dioxide would diffuse from the tissues down their pressure gradient into the circulatory system. And the values and the gradients are pretty similar. So carbon dioxide diffuses down its gradient into the blood. And this is where, Lindsay, we can say, well, what happens to CO2? It may go as just CO2. What else may happen to our CO2? May get converted to bicarbonate ion. Or what? First, carbonic acid, which may dissociate in bicarbonate ion and vice versa, so yes. What else? What's another way that we could transport? Bind to a protein. Which protein could bind CO2? Carbonic anhydrase is an enzyme that makes bicarbonate ion, so sure it can interact there, but there's a transport protein that can transport CO2. So, which one? Hemoglobin. You remember we said hemoglobin can bind not only oxygen, but also CO2? Yeah, nitric oxide, carbon monoxide, all kinds of stuff. So oxygen will diffuse down this pressure gradient. Someone asked me yesterday, do we need to know these numbers? And I would say yes, they are really important to understand. It tells us the gradient and the directionality. If I want to move oxygen out of the blood, I need a pressure gradient. If I want to move carbon dioxide out of the blood, I need a pressure gradient. And we're just quantitating it. What would be the gradient for oxygen? Say between the pulmonary, or excuse me, systemic capillaries in your tissues. About 60. 100 minus 40 is 60. What would be the gradient for carbon dioxide? Depending on the directionality, but the gradient would just be a net of 6. 46 minus 40 is 6. So it's a much smaller gradient for carbon dioxide than it is for oxygen. Any questions before we review how these gases are physically transported? There are two ways that oxygen is transported. The fair share of oxygen just diffuses into our red blood cells and binds to hemoglobin as expected. However, some of it will dissolve in your blood plasma as just oxygen, not bound to anything. However, oxygen is not very soluble. We learned that things that are not, oxygen is not very water soluble, and we learned in chapter 5, molecules that are not very water soluble need a what? A transport protein. Our transport protein for oxygen is hemoglobin. So that just should hopefully tie back into chapter 5. But it's just not completely insoluble, so a little bit can just stay in your blood as oxygen. So I try to use the kind of stock images, so you'll have to forgive my animation skills. But if we, for example, look at the pulmonary circuit, oxygen would diffuse down as pressure gradient. It may, 1, diffuse into our plasma, right? Or 2, the bulk of it is going to diffuse into a red blood cell and bind to hemoglobin. There's really just two ways that oxygen is transported, bound to hemoglobin or dissolved. Those are two possible fates for carbon dioxide. However, we know that there's a third mechanism for carbon dioxide transport. So before I move on, what questions do you have about oxygen transport? Well, if we look at the reverse for carbon dioxide, as I mentioned, it can also dissolve in your blood plasma as just carbon dioxide. It can also bind to hemoglobin, but the preferred route is to convert it to bicarbonate ion, where it is what? Why do we want to convert it to bicarbonate ion?
They can transport it.
Why do we?
It's hydrophilic.
It becomes more hydrophilic. Thank you. Okay. So when we convert it to the ionic form, it becomes more hydrophilic or more water soluble than what it would have been as just plain old carbon dioxide. Let's just review really quickly though. We learned that the bicarbonate ion can be produced really one of two separate ways. One, we said how? I'm going to change. I want to use a different word than dissolve, because I don't want to confuse that as just plain old CO2. So the question was, how can we make? There are two mechanisms for making the bicarbonate ion. We can, one, use an enzyme called carbonic anhydrase, which is localized where? In the red blood cells. So we can form bicarbonate ion if CO2 diffuses in the red blood cells and interacts with carbonic anhydrase. Because this is enzyme catalyzed, we say, well, that's a lot more fast than the other way, which is what? Spontaneously. Where? In the blood plasma. So bicarbonate ion could happen just kind of spontaneously in the blood plasma. So this is an extra way that we can kind of transport carbon dioxide when compared to oxygen. Any questions about that conversion, the use of the enzyme or not? What you got?
No, I have right here.
Okay. Anybody else? Ask away. All right, so I have a similar kind of hokey animation from your textbook. So I'm going to try to illustrate all three types of transport here. With CO2, would diffuse down this pressure gradient from the tissues into the systemic capillaries. Oops, sorry. Where, one, it could just dissolve in our plasma, right? So carbon dioxide out there in the blood plasma, doesn't go in a blood cell, doesn't bind to hemoglobin, doesn't get converted, it's just carbon dioxide. As maybe you thought it was before last week, right? What may be new to you is that carbon dioxide can also diffuse into your red blood cells and bind with hemoglobin. You know, that transport protein. It can bind with hemoglobin is what that little animation is supposed to represent. The second way is it can bind with hemoglobin. The third and most abundant way that carbon dioxide is transported is it undergoes just a transformation to bicarbonate ion. We can enhance that with the use of an enzyme called carbonic anhydrase, which I've just summarized with the abbreviation CA and just put in the blue circles. That'd be an enzyme in your red blood cell. There to bind with carbon dioxide. And what else? CO2 and what else do I need for this reaction? I need a molecule of water. Okay, so carbon dioxide and water can be combined together by carbonic anhydrase to form for us the intermediate. What's the intermediate? Which one? First, before it goes to bicarbonate ion, we have an acid. What is the acid? Carbonic acid, okay, or H2CO3. That acid can quickly destabilize into the ionic form. That's when we can break it into bicarbonate ion and hydrogen ion. So the byproducts after the carbonic acid is formed, bicarbonate ion and hydrogen ion. The bicarbonate ion will likely not stay in the red blood cell. We're trying to make it so it's more water soluble, so we want to put it where there's a lot of water. Where would there be a lot of water? In the what? You guys might know. In the plasma. So it's an ion, so I want to take it from the cytosol of my red blood cell and put it here. What do I need? A transporter. So I just pump it out. It's charged though. This isn't a muscle cell, it's not a nerve cell, so I don't want to change the polarity. So what should I do if I want to keep the polarity the same? If I take something negative out, I put something negative back in. Okay, so just keep it equal. And so what happens is bicarbonate ion will be pumped out and chloride ion would be pumped in. This is called the chloride shift. The chloride shift occurs at which type of cells? Our red blood cells. And we're sending out what? We're sending out bicarbonate ion. To the plasma, right? And we're bringing in what? Chloride ion in. That keeps the neutrality of the cell. So we don't want it charging and repulsing and doing all kinds of stuff. We just want it to go with the flow. That is a failed attempt at an @ sign. Sorry.
And what happens in the plasma?
No, it happens in our red blood cells. It happens across the red blood cells. The red blood cells are sending bicarbonate ion out into the plasma. Maybe that's where you're going. Takes it from the inside of the red blood cell and just takes it to the outside of it, which would be your plasma. It takes from the plasma and pumps into the cell chloride ion to keep the red blood cells charged neutral, or what it needs to be.
As a pump?
It's an anti-porter. It is not, I do not believe it's active though. I need to verify that. And because it's pumping it, it's sending it out. So I don't think it's active. Does anybody have it? You'll have your textbook. Someone can look it up in the background. I don't believe it's active. It may be. Look up the chloride shift in the textbook, W chapter 17. I'm gonna have to look that up for you, Lisa. I think it's passive, but I could be completely wrong. I'll look that up for you, Lisa. Good question. Additional questions give me a question I can answer. So the takeaway is, does most of our carbon dioxide just diffuse in the blood and stay as CO2? No, some may, sure. But most of it will what? Most of it is going to get converted to bicarbonate ion. Could happen in the red blood cell like I have here, or it could happen in the blood plasma as well. A third fate for carbon dioxide is what? Bound to hemoglobin. Right. So we know that our gases are carried multiple ways. And then we also know that, right, experiencing this class, our respiration, just like everything else, has to be controlled. And this is predominantly going to be controlled by your autonomic nervous system. But you know that you can voluntarily override your respiratory patterns, right? When we did our respiratory law of the deep breath, you could do that. You didn't have to just wait for you to go run or something like that. And so it's going to have a standard kind of reflex arc. For a reflex arc, I need what? I need a stimulus. I need a control center. Between the stimulus and the control center, I need a receptor. And I also need what? An effector organ. And so that's what we'll summarize with an image in just a moment. So our control center for respiration is where? Where's our control? The medulla oblongata of the brainstem. This is very similar what we saw in the the circulatory system. Sympathetic fibers tell your respiratory rate and volume to do what? What effect would the sympathetic nervous system have here on your breathing patterns? Increase it. Okay. And the parasympathetic nervous system would decrease. And so, what do you think your respiratory system, your sensory nerves might monitor to determine the output by the respiratory system? What do you think we could maybe monitor? Volume. Heart rate indirectly is going to be tied to it. Yes? What else was added? Our gases. And definitely oxygen, carbon dioxide. pH. We know that carbon dioxide changes our pH. So your body's continually monitoring those themes, talking to the medulla oblongata, and the medulla oblongata is talking back out to your diaphragm, intercostals, etc. And this is summarized for you in Figure 17.7. I didn't provide it because I kind of ran out of room and it went to a whole other page. But Figure 17.7 summarizes what you guys just articulated. To control my breathing patterns, I need specialized receptors that communicate with my medulla, which is my control center, medulla oblongata, which affects my breathing pattern. And just like many of the other organs that we've seen this semester, the respiratory system is dually innervated. Sympathetic nervous system increases respiratory activity. Parasympathetic nervous system decreases respiratory activity. That looks like all that I was going to present to you for Chapter 17. So before we transition to the renal system, what questions do you have over the respiratory system? We'll conclude the respiratory system here.